welcome to our November meetup. Just a reminder that these sessions are recorded, and we just ask that everyone could place themselves on mute, and we'll open up for questions at the end. Hi, my name is Clara and I'm the Office Coordinator here at KISPE. The Open Source Satellite Programme holds regular meetups on a wide range of topics related to the space industry, from applications through to modelling, technical topics, hardware related, and the wider space ecosystem. Last month, John gave an overview of the open source satellite and why it's important. If you missed it, it's now available on our YouTube channel. This month, we're excited to introduce Paul Madle and Jamie Bayley from KISPE, along with guest speakers Brian Yeomanns from the University of Surrey and Andy Dachs, who is an OSSAT collaborator, who will be demystifying the CCSDS communications protocol. A big thank you to Andy for joining us all the way from New Zealand, where it's currently 5:30 a.m. So let me start by handing you over to Paul.
Thanks very much, Clara. So yes, I'm Paul Madle talking to you from the Open Source Satellite Programme. And I'm excited to be talking to you about the CCSDS communication stack and the development that we've done, that we will be releasing open source as a sort of CCSDS communication stack for the spacecraft and for the ground as well. So today, I'm going to introduce you to CCSDS if you're not already sort of familiar with it, what it is, and that kind of thing, and then what is our implementation of it. And then we're going to be going into a little bit more detail about various parts of the interesting parts of the protocol stack that we've integrated or implemented. My colleague Jamie is going to talk us through something called COP1, what that is, why do we need it. My colleague Andy, all the way from New Zealand, thank you very much, Andy, is going to be talking about CFDP, which is ways of transferring files around from the ground to the spacecraft. And then finally, my great colleague Brian will be talking through our ground offering, which is a piece of software that we've adapted called Yeomanns, or Yet Another Mission Control System. So just who these people are. Andy is as I say, in New Zealand. Actually, he used to be my boss, but he's come back. And when he found out that we were developing an open source design for a spacecraft, he wanted to be involved, and he's been very kind. And he has developed over COVID. Actually, it was a bit of a COVID project for him. A CFDP implementation written in C code, and we've integrated that into our code base. So that's Andy. Brian is a great guy with loads of experience of ground infrastructure for spacecraft, lots of experience with amateur satellites, and as I understand it, the work he's been doing with CCSDS protocols has proven quite helpful for the University of Surrey, where Brian works, and we've done a little project with the university to develop the ground side of their open source offering. And then there's two people from KISPE, Jamie, who is instrumental in integrating all of the onboard software together, both something from another open source provider, and Andy Dachs, who developed the CFDP stuff. He brung it all together, integrated it, and got it running on an STM target, and that's what we're running with for the open source satellite. And then there's myself, who kind of just sort of brings it all together, really, and makes sure that everybody knows what they're supposed to be doing, and that kind of thing. So yes. So an introduction to CCSDS. What is CCSDS? It stands for the Consultative Committee for Space Data Systems. It has a website, ccsds.org, but it is basically a set of, it's an international organization encompassing NASA, ESA, JAXA, lots of the world's sort of space organizations, and they come together and they issue they call it a set of recommendations as to the way that spacecraft could talk together, spacecraft talking to the ground, and how space data can be routed around on the ground as well. So there's a whole suite of different documents that make up a set of CCSDS protocols. It's not the only way to speak to a satellite. There are other ways as well. But you know, we when we were developing the open source satellite, we recognized that CCSDS is probably the most recognized communication standard or set of recommendations for space communication. So we wanted to make something that was kind of able to work with the largest amount of the world's ground infrastructure, and so we chose CCSDS. And the protocols actually have a long heritage. They actually predate things like internet protocols like TCP/IP and FTP and all of these kind of things. So they've got a long history. Yeah. So as someone who's kind of come into the world of CCSDS, you know, having never really experienced it before, my take on it has been that there's a lot of good descriptive documentation that takes you through in great detail about you know, how the protocols work, but it can be quite difficult to sort of get to grips with the documentation. And I think it's probably true to say that most people who come to experience it probably do so from the perspective of having an implementation of CCSDS, some kind of, you know, you start work as a ground systems engineer or assembly integration test engineer or something like that. And so you pick up how CCSDS works. But it's not so easy to engage with if you're sort of like me, coming from it completely blind and trying to read these documents and understand it all. And so the reason for today's call is because this is the video I wish I had seen early doors. You know, we're in the days of YouTube now, so you know, we should be able to go on YouTube and hear an introductory video that's helpful. So my hope is that this video is helpful for anybody who's like me. It's the video I wish I'd seen about a year ago. It is CCSDS for Dummies, and yes, that means I am a dummy. So what have we implemented and what do we have as part of a CCSDS implementation? What we have basically what you can see here is a diagram showing you the OSI layers for communication stack in the middle. To the left, you can see the parts of the CCSDS protocols that we've implemented, you know, both on the spacecraft and on the ground. And on the right, you can see a slightly more detailed breakdown of these protocols. So just taking it through, I don't know if you can point at the various bits there, Jamie, but from the bottom up, you've got these kind of orange boxes. So typically, you know, right at the bottom, you've got a physical layer. In our case, that's wibbly wobbly waves in the radio, you know, in the radio realm. These signals that are passed, you know, going between space and the ground. And then above that, you have synchronization and channel coding layer. So that's the demodulation, modulation type area where you're basically sort of taking those wibbly wobbly waves and creating digital signals, ones and zeros. And now the implementation that we currently have, which we will be making open source, is from that sort of layer upwards. So on the space side, you've got a Datalink layer, which encompasses telecommands. That's commands going up to the spacecraft, and telemetry, that's data coming down from the spacecraft, and also some helpful things that allow you to sort of ensure that a command which you want to send to the spacecraft has actually got there, which we'll be describing in a little bit more detail in a moment. Then above that, you've got this kind of thin layer called the Space Packet Protocol, which, you know, doesn't do a massive amount, to be honest. It just packetizes the data. But what we've done is we've taken a great bit of software that was developed by another open source organization called LibreSpace. They developed something called OSDLP, which is available open source on the internet right now. And we've basically forked that and developed it for our purposes on the open source satellite. Very much thank you to OSDLP, to the folks at LibreSpace for that. It's very, very helpful. Now, above that layer, we have this, a few different things. Probably most notably, from the perspective of today, is CFDP. So CFDP is our file transfer protocol. So it's how you transfer files to and from the spacecraft from the ground. Now, there really wasn't a sort of complete open source implementation of this that had all the features that we want. There are open source implementations of it, but not one that featured the bits that we needed. And so my colleague Andy Dachs has developed that for us, and we'll be making that software open source. He's joining us today, and he'll be able to take you through a little bit of that. And then far over to the left, we've also got a ground implementation that is also open source and is currently available, and it's called Yet Another Mission Control System, or Yeomanns. And we've developed, we've basically taken Yeomanns as is, which already handles CCSDS communications, and we've adapted it slightly to meet our needs. And again, that fork will go open source. So without further ado, I will hand over to my colleague Jamie, who will take us through COP1, what that is, and that kind of thing. Jamie's been working on the open source satellite for around 3 years now, and he's become a very, very valuable member of the team. And as I say, he's done some great work integrating all this together. So over to you, Jamie.
Hi everyone, I'm Jamie. I'm another software engineer here at KISPE, and yes, I am another dummy. I didn't have a clue about CCSDS before we made this implementation, and that was my first kind of step into the world of CCSDS and ground space communications. So I kind of took on this and integrated everything that was done by collaborators together into our onboard computer, and managed to get it to work with our ground station solution that Brian was doing. So yeah, I'm going to talk a bit more about the COP1 protocol that we saw in the previous slide, which is this little bit here. It's a part of the space data link layer. So this is for telecommands going up. So what is COP1 protocol? It's a protocol for ground space communications, and it's part of the CCSDS stack. It's not something that comes as a standard. It's something you can kind of add in if you wish. And its whole reason for being is that it ensures that commands that you send, if you enable it via COP1 for a telecommand, that telecommand will get to the spacecraft. And it also ensures that if you send multiple, that it gets there in the sequence sent. So if you need to send multiple telecommands that need to be executed in sequence, it will ensure that that happens. And also another benefit of having this is that it copes with the unreliability of a radio link, which is something that you'd usually see with spacecraft. So to talk a bit more about how COP1 works, there is an idea of this number that we have. And there's one that exists on the ground, and there's one that exists on the spacecraft. These are called the V numbers. This is how COP1 works. The idea is that all these numbers need to be synced together so that we can ensure, so that we know that the telecommands have got there. So the ground has a VS number, the spacecraft has a VR number. Those are numbers held in the states on the ground and on the spacecraft. And then there's these N numbers, and these are the numbers that exist in the actual messages going up to the spacecraft and coming back down. So VS on the ground, NS on a message going up to the spacecraft, VR on the spacecraft, and then NR on a message coming back down to the ground. So how these numbers work is that we need to synchronize actually to the VS number on the ground. because when you send a telecommand with COP1 enabled, that VS number gets incremented by 1 and then sent up as the NS number to the spacecraft. If the spacecraft receives it, it will increment its VR number by 1, and then the response NR number coming back down will also reflect that. So then the ground knows that if the NR number it's received matches its own VS number, that the message got there. And this NR number can come down in a telecommand response, or it can come down as part of normal telemetry that's coming down as well. So to also facilitate this, there are 2 different state machines that we have as part of COP1. You have FOP and you have FARM. FOP is the state machine that exists on the ground, and FARM is the one on the spacecraft. FOP is on the ground is the one that has all the brains that can be moved between lots of different states and lots of events happening, and can do quite a lot of nifty stuff with retransmitting and telecommands if needs be, and lots of other stuff I won't get into. And the FARM on the spacecraft is quite simple. That's done in a way so that the ground handles most of the brains. We want the spacecraft to kind of be as dumb as possible. So they each have different they use different states, and that's how that works. So I'm going to take you through a couple scenarios now of how COP1 might work in a real application. So our sunny day scenario is a simple one to start with. This is where everything's gone well and the telecommand has got there. So imagine the spacecraft is coming over site of ground station. We begin our downlink session. There you go. We're receiving telemetry frames from the spacecraft, NI 0. And then we go, oh, I want to send a telecommand to the spacecraft. So I increment my VS number on the ground by 1 and send the telecommand with the NS number reflecting the VS number on the ground. That gets to the spacecraft, and the spacecraft goes, oh, I've received that. That's nice. I'm going to increment my VR number by 1. And then the next telemetry frame coming down will reflect that with an NR number of 1. The ground goes, yeah, that's fine. That must have got there. And then you just receive successive telemetry frames, assuming you don't send any more telecommands until the spacecraft goes out of range of the ground station and the downlink session ends. So that's fine. That's sunny day scenario. So now I'm going to go through a rainy day scenario. So this is command retransmission. This is what will happen if a command does not get there. So spacecraft's coming over the ground station, downlink session begins. We're going to start receiving telemetry, and then, oh, I want to send a telecommand. I'll increment my VS number by 1 and then transmit that as the NS number in the telecommand going up, but it's not got there. And that is reflected. The spacecraft never gets it, and therefore it does not increment its own VR number, and the NR number in the responses is actually less than the VS number on the ground. So the ground look at this and go, oh, something's gone wrong here. I'm going to retransmit. So it retransmit that same telecommand again with the NS number of 1. Spacecraft receives it this time, and then increments its own VR number to match that, and the response shows the same. You receive several more until the downlink session closes. So that's command retransmission. So now I'm going to take you through another rainy day scenario. So this is for out of sequence. So this is when you send a couple telecommands, but one of the earlier ones you send doesn't get there, but maybe some of the later ones do. Remember, COP1 ensures that all telecommands sent are executed in the order sent. So spacecraft is coming over the ground station. Downlink session begins. We are going to receive telemetry. And then we decide I'm going to send a telecommand now. I'll increment my VS number by 1, send that telecommand. It does not get there. But in the meantime, I want to send another one. So I'm going to increment by VS number by 1 again and send that. This second telecommand has the NS number of 2 in it, which actually gets to the spacecraft. The spacecraft itself will ignore this. It will not execute it because it's out of sequence. Its own number is not actually one less than its VR number is not one less than the NS number sent. Therefore, we still get another telemetry frame with our NR number as 0. The ground goes, the NR number is 0. Therefore, I need to retransmit the first one, which gets there, increments the VR number by 1, and then retransmit the second one, which gets there. VR number is incremented by 1 again. And then the NS number comes back as 2. Happy days. It was the telecommands were retransmitted in the sequence that was meant, and they got to the spacecraft, which accepted them in the sequence sent and executed in the same sequence. So this is also called, this is an automatic retransmission scheme called go back N. So to talk about this a bit more, COP1 is go back N. This means that if you transmit multiple things and the first one doesn't get there, but 2 and 3 do get there, then it will go back to the first one and retransmit them all again. This is good for telecommands that need to be transmitted and executed in sequence, but it's not so good for things like file transfers. Because if you're sending a lot of file data up in sequence using COP1 and you miss the first one, but the next 500 get there, well, you're going to go back to 1 and start all over again, wasting the 500 other file packets that got there. So CFDP, which my colleague Andy is about to talk about now, uses a scheme called selective repeat, meaning that if the first one doesn't get there, but the next 500 do, the spacecraft will send a message down to say, I missed number 1, please retransmit number 1 for me. So take it away, Andy.
Thanks, Jamie. That was a great introduction. So yes, as Jamie mentioned, I'm going to talk a little bit about how we send bigger blocks of data. Usually they'll be in the form of files. And the mechanism we have is the CCSDS file delivery protocol. So I'm going to cover quickly what it is, probably more importantly, why is it needed, and I'll go a little bit into how it works, but I'll just try and point out the key things rather than go blow by blow detail. Can you on Jamie? But starting with why is it? Why do we need it? Before we talk about any of the other things. As I mentioned, it's to move those large blocks of data around. Jamie's covered the telemetry and telecommand, but when we get to larger things like log files or command files or pictures, we need a mechanism that's going to handle those larger blocks. But what makes this one special? We're used to sending files, and browsing a web page, anything is really sending files. So why do we need anything particular here? Now, Jamie's covered a couple of reasons there. We're used to opening a web page, and essentially the internet is assumed to be a reliable transport. Either because it's over something reliable itself, or because it's got those retry mechanisms that were mentioned. But in a satellite, we've got effectively unreliable communications, and that could be for a number of reasons. It could just be noise on radio links, but it could just be because the satellite comes and goes as it arrives over the ground station or leaves again. So think more like trying to transfer a file on a train with 1 bar of signal going through tunnels occasionally. How do we make efficient use of the communications bandwidth, which is limited and precious, and still be able to get our data through reliably? There are some other scenarios which come up quite a lot, which is that the up and down links are not the same. Often we would have a fairly fast downlink for sending image data, but we might only have a very limited bandwidth uplink, which is typically used for telecommanding. Now, many of the existing, internet type protocols don't work particularly well when you have different up and down links. And the other one, which we're not really encountering here because we're talking mostly in a sort of LEO context. But if you go into deep space networks, you could have very high latency between the time you send a message and the time it's received. And CFDP is used in all of those contexts. But here I'll concentrate mostly on the LEO type environment. Can you go on, Jamie? So what is it? There's a lot of terminology in here. When you start reading the standard, you'll come across these terms like a procedure and an entity. So in CFDP, every say the ground station or a satellite would be an entity. An entity's got an associated file store, which is where the data is kept. There's a communications mechanism that we've spoken about. That's often referred to as a UT layer. And there's a notion of a user. Now, obviously on the satellites, we're not generally talking about a real person. That's going to be the onboard computer. But we are able to send messages to that onboard computer, and we can get that user to do operations for us. Like we could ask them to copy the file to another place. We could delete the file once we finish with it. We could rename it. All those things you'd expect to do with a file. And then the last piece on this is the database, the MIB, and this makes CFDP extremely configurable. There's a lot of different options. Although the standard itself talks about how, what goes in this database, doesn't really specify how you store it. In this implementation, it's done as a JSON file, but that could be any kind of database or flat file store system that allows you to configure it. I'll talk a little bit about some of the options available, but there are a lot, and you would have to go through the CFDP standard to see all of those options. But we'll talk about some of the main ones. All right, so how does it work? So, like I said, there's a lot of options. There are 2 main classes of file transfer, and they kind of correspond to whether you've got a nice reliable data link, that'd be class 1, where it basically just sends some metadata, it gives you the file name and what to do with it, and then breaks the file into chunks and sends them. That's really efficient. Because it's broken file into blocks and they're numbered, you can resume transfers and pick them up where you left off. It does handle asymmetrical links really nicely. In fact, you don't strictly need a transmit part at all. You could just listen to a class 1 transfer and get the whole file. And because of that, you don't have any problems with high latency. But it does assume that the underlying communications is reliable enough, or that you're sending something like a picture where, if you lost part of the image, you'd still want the data, but not so good for sending something like firmware or command files up, because you would have no guarantee that you'd actually got the whole thing. So that's where class 2 comes in, and that's got the ability to recover missing data. It's a selective repeat mechanism, as Jamie mentioned, and this works really well with unreliable links. It doesn't put a lot of demand onto the communications protocol stack at all. It will work with simple messaging with no repeats at the link layer. Jamie? Okay, this I don't really want to go through blow by blow, but similar concept here. You have the user talks to their own source entity. The entity talks to the one on the other side, the destination entity. So that, say, would be the spacecraft, and the destination user would be to the satellite onboard computer itself. In this scenario, so this is an example of immediate NACs. And again, one of the ways that CFDP can work. And essentially what happens here is you start transferring the file, and it sends these blocks out, PDU1, PDU2, PDU3. If it comes across a situation where one of those data blocks doesn't get through, of course, the ground side doesn't know that, it carries on. On the spacecraft side, if it detects that it's now got a hole, it got, in this case, it missed one PDU, so now it has it knows it missed something. Thanks, Jen. It will then, if it's configured for immediate NAC mode, will immediately send a message back down to the ground with this NAC saying, "Hey, look, I've got a hole. I missed something here." And the ground station will receive that, recognize that there's a hole, and send it back. Now, and then you fill the hole, you carry on, you send the data, and then at the end there's a conversation about it's the end of the file, and acknowledges it was finished, and everybody agrees that it's got the whole file through by checking the checksum on the file. What's notable as well is the indications that go back and forth between the entity and the user. So there's progress notifications, as well as indications that things have started and stopped. Now these would be, could give you progress bars. They could give you notifications that a new file's arrived, that your downlink is complete. And this is the way that you connect the stack to your application. Or if you have a real user, there would be the way that they would notify your user that something's happened. But it's also used as the so these are the callbacks in the stack that allow you to connect up to it. The first message, the PDU, is an important one because that contains information about the file, so like its file name. If that doesn't arrive, the other side doesn't know that what the file is going to be called until it'll request that as well. So eventually it will have it by the time you get to the ACK at the end. But it also contains messages for the user, and also contains kind of automated messages. So the messaging system is used to both send textual messages to users, but also send these operations like rename, copy, and in the case of the puts, can actually just ask the far side to do some other operation. So a put is you could just put something with a PDU with just the metadata. So you could say hey, Spacecraft, I want you to do this operation, and the operation could be to send me a file back again. So there is a notion of file transfers with no file data other than the metadata. It's purely just the operations. But the bit I really wanted to highlight here, and the bit that I find makes this protocol somewhat special and interesting compared to other ones, is the NAC packet. So in this example, it's kind of made it look like the NAC is just a simple, request the next packet. But actually, that's not the case. So Jamie, could you move on to the next thing? What the NAC packet itself was actually a list of holes. So each side maintains a list of what it thinks are the missing bits of data in the file. On the source entity, that starts out as being one big hole, and it tries to fill that hole in. On the sync entity, so the one that's receiving the data, the same thing. It knows it's going to get a file, but it has got no data, so it's got one big hole. And then as we go through, the source entity starts sending data, so it starts filling in its idea of what holes are left. And the same with the sync entity. When it receives the data, it starts to fill in missing bits. If you miss a packet in the middle, like we had in the previous example, you'll end up splitting your hole. So you'll end up with, I've got some data, I've missed some, I've got some more data, and then I've got the rest of the hole. So now I have two holes. And you can imagine as you start receiving data but missing things in between, you're going to land up with a long list of holes, and that's what gets sent back in those NAC packets. And when the NAC packet arrives back at the sending end, it updates its idea of what holes are left and starts to fill them in again. And it's this mechanism which is the real power of CFDP. It allows you to break the dependency between a kind of a one-to-one symmetrical link where you're sending lots of data back down as well. As long as the sender side has got enough information about what holes there are, it can just keep going. And there's no particular time dependency on getting these NACs back. And so some of the other mechanisms, like or some of the other options I mentioned in that MIB, are things like deferred NACs. So you don't send these NACs until later in the process. You let the source side transmit for, send the whole file, and then you send back a list of all the things you missed. And that makes it really efficient and gets you away from this need to have, as I mentioned, the symmetrical links. You can deal with quite highly asymmetric data links. It's a concept a little bit more difficult to get your head around. So if you're starting to read CFDP, this would be a place to look into the way that these NACs work. But to me, this is the magic in the protocol, and this is what makes it really interesting to work on. So thanks, Jamie. Paul, we can move on to Brian.
Just unmute myself. Hi, thanks, Jamie. Thanks, Andy, for that. Okay, just a quick overview of the ground-side software that we've been using, which, as Paul said, a rather wacky acronym, yet another mission control system. Well, why? I'm the ground station manager at the University of Surrey, and I guess the first question is, well, why are we interested in Yeomanns? Well, actually, we have our own completely bespoke mission control system, but the problem we have with it is it's about 8 years old, and it essentially needs a complete rewrite to make it do what we'd want to do now. So the comparing that situation with a scenario where we've got, pretty much 95% of what we've ended up with here is being supported by some lovely people in space application systems, and we don't have to support it. That's really attractive. And the other reason why this was an interesting project for us is one of the things we're currently involved in is receiving data from Deep Space Network craft. And surprise, surprise, these big mission craft all use CCSDS in one permutation or another. So actually, getting your head around how the data structure works, data structures work, has proved very valuable in that exercise. So what is Yeomanns? Well, it's a Java-based open source framework, and as I said, it's developed by Space Application Systems in Belgium. Completely free, no cost at all. It's not an app. It's a series of components, and one of the benefits of that is you can distribute those components around. So you can have the server in one central place. You could have multiple users who are using the web user interface. You can be accessing the server via the API using Python scripting or other coding mechanisms that can use the HTTP API. So it's pretty flexible. What does it do? Well, it does the usual mission control system stuff. So, you know, it can construct commands, send them with verification checks. It can capture telemetry coming back. It can interpret the telemetry. It can do archiving. It can do monitoring. So if you're checking telemetry values within certain ranges and you're off that range, it can trigger an alarm. It can do some very nice graphs as well, which so a load of things that are, I think, really useful and helpful in the context of, you know, an operator sitting there looking at the screen, you know, is getting a lot of useful information out of this. And obviously in the context of this discussion, it's got lots of CCSDS stuff built into it. So TNTC data frames, it does. COP1, we've talked about, it already does. Space Packet Protocol, it does. CFDP, it does. To some degree, and just kind of re-emphasize the point that I think Paul made a little while ago. Remember, CCSDS, it's a set of recommended standards. So you've got this kind of wiggle room thing here. And one of your early questions, if you're going to get on to using Yeomanns with as the ground side with the space side, is kind of, you know, look to where the differences might be. And it's not, as you'll discover, it's not that these are necessarily a big problem, but you'll find some subtle differences and subtle distinctions that need to be catered for on one side or another. What does it not do? Well, for example, there's a thing in the CCSDS standard called MAP, multiplexer access point, which is like a second layer of multiplexing. In kind of standard CCSDS, in TNTC data frames, they use a concept called virtual channels. So there's one physical channel, your radio channel, and that can carry a number of virtual channels. A map allows you to go down even one step further, so you can multiplex channels within each virtual channel. Well, Yeomanns doesn't do that. I suspect you need quite a complex mission before you're even needing to think about that, though. So it's probably not a big issue in practice. The other point I would mention, again, just a flag, is it really doesn't do automation. So it's best suited to an operator who's sitting there and actually sending commands. The provision to send multiple commands or command stacks is really quite limited. So it'll do basic stuff like send command 1, you know, wait 5 seconds, send command 2, and so forth. But it doesn't, within Yeomanns, do conditional execution. So, you know, a typical thing you might want to do is you send a command to reset the system clock, you want to check it has actually reset before you send the next command. So you want to get some a response back, check it's right, and then conditionally execute the next command. Yeomanns won't do that itself, although as we'll come on to talk about, it's actually not that difficult to craft some external scripts that interact with Yeomanns that will provide that thinking power and basically get you to do conditional execution. Okay, Jamie, next slide, please. Okay, so what's it like to work with it? Well, I found it quite a good experience. How do you get it running? There's a quick start example out there. Literally, you can get that on your machine, fire it up, and off it goes. It's got a very basic simulator in there, but you can get a real working example that you can interact with in maybe half an hour. And then to kind of develop from there, you can use a series of examples that the Space Application Systems guys have developed. So you can replace your quick start files with the example files and get something a little bit more complicated working. So, you want to do CCSDS frames and you want to try COP1, there's an example in there and you can get it going. Those quite a number of them use a more complex simulator that is embedded within those examples packages in Yeomanns, and actually, that gives you quite a decent experience of how these things work. So it's a kind of incremental process. You don't necessarily, you can get something going without investing a huge amount of time and effort in it, and you can kind of incrementally kind of feel your way around it and see what bits do what, if you like. So I think that's actually quite a good and rapid way of learning the system and how you interact with it. In terms of a couple of recommendations, I personally think it's a good idea if you're going to use Yeomanns to do fairly comprehensive logging. So log the traffic, basically. You will find that very useful. If you get things that aren't working, it's easy to configure the logs. That will capture in nice ASCII hex all your traffic, and you'll be able to go in there and look at what's going on. That is, if you've spent a bit of time reading the CCSDS documents, particularly the just a few pages that describe the actual structure of the packets and the header structure and so forth, because you might find early on this is all a bit intimidating and confusing, but I promise you, if you spend a little bit of time and effort on that, you will start to figure out what's going on, and then you can really very rapidly look at the data that's flying backwards and forwards. You can recognize features of those headers, and you can go, oh yeah, I can see A, what's going on, and I can see what's not quite right about that. What's the support like? It's pretty good. It's all online. Everyone sees everyone else's question and reply. Pretty responsive, often staggeringly responsive, actually. So, half an hour sometimes you got a reply from those guys, and the support is from people who actually wrote the code. So they know what they're talking about. The documentation is also pretty good, but like all documentation, it won't answer all your questions, because it never does, which is why there's this online support facility, basically. What else can you do? You can wrap it in a Docker container if you like. It's pretty straightforward to do that. So when you deploy it, you're not really limited to any particular machine or context or anything. Getting into making modifications, the kind of early stage changes, it's actually quite straightforward, because mostly they're implemented via changing configuration files. These are technically YAML files, so they're in plain text really, and again easy to easy to understand what's going on, and secondly, there's good documentation on what all the provisions do. Probably anyone getting as far as implementing YAMMs is going to need to at least write a little bit of Java code, because you're probably going to not want to use the particular version of Space Packet Protocol that the YAMMs examples use, which is actually based on the ISS setup. But you will find that there's examples there of how you write what are called pre-processors and post-processors. So these are two tiny bits of code, a couple of Java classes that are, kind of next to the radio, if you like. So on the way out, the command, the last thing it does is it goes through the post processor, and similarly the telemetry coming back, the first thing it does is it goes through the preprocessor, and they handle some basic stuff like the time configuration, or catering properly for the time configuration that you've decided to adopt in your space packets and so forth. What else do you need to think about? The mission database. So if you like, what represents your commands, or rather, how do you code your commands? What does the telemetry coming back, what does it mean? There's two ways of doing that in YAMMs. You can use XTCE, which is a kind of basically a whole kind of setup of standardized ways of representing this information in a space context. It's basically XML. Or you can be a bit old-fashioned and set everything up with an Excel spreadsheet. Both of those work perfectly fine in YAMMs. This is a kind of subjective thing, really. I mean, I personally don't find XML very easy to understand or kind of review, whereas using a spreadsheet, I think actually you can construct these things so it's easier for a human to review. So that's my preference, but others may feel differently. And the final point I want to make on this slide is the web user interface is pretty comprehensive, but we'll talk about this in just a moment. There is also this REST-based API and a really quite comprehensive client wrapper for the API, which is a WebSockets client-based wrapper written in Python that does quite a lot of stuff that the web UI hasn't implemented. So Jamie, if we go on to the slide on the enhancements. Okay, so I'll skip through these and just kind of describe what they do. We won't have time today to go into the detail of how all this works, but at least this should give you a flavour of the extra bits. Custom Space Packet Protocol structure, that's kind of in a way not an enhancement. I think that's just something you'll have to do, as I talked about a moment ago, to, you've chosen your particular format for the headers for the space packets, and that's just implementing that. So you'll need a bit of bespoke code for the pre and post processor classes. Custom TC acknowledgement, additional to COP1. What we wanted to do here is Jamie talked about COP1, and obviously it checks whether a command has been received, and if not, resends it. But it kind of happens under the hood, if you like. So what we wanted to do is to add some extra capability. And to do this, what's happened is that the spacecraft, when it receives a command or an uplink message, it sends a specific ACK message back, and that's providing some checks within it. So, did we send that command to did our addressing within that command correlate with what the spacecraft is expecting. Did the command pass the CRC check? So we got messages coming back, and actually Yeomanns has the capability to fire up some, basic JavaScript-based logic checking when it receives these commands to, basically then turn those into giving the operator, giving the ground side quite a lot more information on, were these checks passed and when were they passed? So the result is when you send a command, the command fires off. Yeomanns already does some ground side checking, so it goes, oh, okay, have I validated this command? Is it, what the system's expecting? Has it been sent it? So it gives you that information with timings, and similarly, it'll give you timings acknowledging the information coming back from the ACK message that says, oh, did it pass the CRC? Yeah. Was it sent to the right address? Yeah. Or if not, it will tell you. So rather than COP1, where the system will just kind of blindly try and keep retransmitting, it's giving you more information. If something's gone wrong, it's telling you what has gone wrong and therefore giving you a clue as to what you might do about it. Okay, now the next one, the bootloader file upload. This is kind of an example of what I was talking about a moment ago, of using the API rather than Yeomanns. And the reason for looking at COP1 file upload is that you might think, oh, okay, CFDP is for file upload, but it's quite a complex set of procedures, algorithms, quite a complex system. So we wanted to see if we could do something really simple, which is basically just taking a file, chunking it, and sending it using COP1, and basically get to the same end result, but in a slightly less sophisticated way. But this needs a much simpler set of basic coding on the spacecraft to achieve this. So essentially what it does is what I just described. So it takes a file, it breaks it up, it targets a speed for sending each chunk, which is commensurate with the data rate that the link can absorb. It monitors the COP1 status on the ground. So if it starts getting retransmit messages, it slows down, basically waits for that to clear and then carries on. So it does kind of some basic reactive conditional automated management of the traffic. So it's kind of, I think, quite a good example of adding an enhancement to Yeomanns, where Yeomanns itself doesn't do that stuff, but you can write an external script that handles that for you. Okay, custom telemetry display. So what's this all about? The scenario here is where the operator is going to send a command. He wants to check a particular parameter. Maybe he's a bit concerned that it's out of scope or whatever, and he wants to be able to see clearly the response to that request. He doesn't want to be bombarded with mountains of data. He doesn't want to be having to take it offline and analyze it. So we had quite a think about how to do this, and there are ways built into Yeomanns that can give you what in Yeomanns parlance are called parameters, displays of parameters. But and also there's a separate Yeomanns product called Yeomanns Studio, which also does a somewhat similar thing. And they're fine if you know exactly what you want and you can kind of set it up in advance. But what we wanted to achieve here was essentially to be able to just generically make a telemetry request and then have the system display whatever parameters came back from that telemetry request. And that could be, you know, one out of dozens of different types of request. So I haven't got time today to explain how it all works, but it uses the same Python accessing the API scenario that we've just talked about. So it basically tracks the command, checks if it is a telemetry request. If it is a telemetry request, it figures out from the mission database what parameters are expected to come back down. It then listens for the parameters and then it displays them in a browser. So we basically run a Python-based backend that collects that information, and then we just fire that off into a JavaScript browser to see your requested telemetry. And finally, on this slide, just making a couple of points about the CFDP implementation. And here, what we wanted to do was to minimize the overhead, because essentially CFDP does everything for you already. So everything is already packetized in PDUs. It's managing, there's no need for COP1 because it's already managing the data flow perfectly fine by itself. So we didn't want a scenario where we were adding any extra framing or packetization or anything like that. And that's what we managed to achieve. It's a sort of slightly unusual way of doing it, because what we're essentially doing is we're kind of fooling Yeomanns into thinking it's handling regular packets, but these are packets that actually have no processing whatsoever. So there's no header, there's no timestamp, there's nothing. But Yeomanns just gaily handles them as though they're packets, but we don't add any overhead as a result. Okay, and that is me, Jamie. Thank you.
Well, thank you very much, guys, for giving us the overview of these different parts of CCSDS protocol. Just very briefly, just a couple of thank yous. Thank you very much to the people at Libra Space for their implementation of the various parts of the protocol stack. Thank you very much to Di Stanton, who is he's just started his video, but Di has been very, very helpful in kind of demystifying some things for us along the way. And thank you very much for the folks at Goonhilly, who've also been very helpful along the way. So Goonhilly Earth Observation Centre in Cornwall, those guys have been really, really helpful to us. So just to conclude, we have developed a open source solution for CCSDS comms that is suitable for a low Earth orbit spacecraft, and this includes space-side onboard software, but it currently excludes the channel coding and synchronization layers, and it also includes a ground-side solution based on Yeomanns, which has been adapted and forked from the Yeomanns baseline. And we're hopeful to make all of this stuff open source to the wider community within the next 4 months. So that's where we are. Thank you very much for listening. I know we're kind of very low on time, but I'll hand back to Cara and just say thank you very much for listening. I hope it was helpful.
Thanks, Paul. Just wanted to open up if anyone has any questions as well. Just have a look if there's anyone that's got anything for us.
Yeah, I wanted to add a couple of things.
Yes.
It's worth going to the CCSDS site and reading the CFDP Green Book, which kind of demystifies a lot of the stuff in there. The Blue Book is written in open standards speak, so it's written for unambiguity rather than understandability, if you like. But if you really want to get into all that stuff, it's worth reading ISO 7498, the Open Systems Interconnect Reference Model, if you want to really get up yourself about the terminology, which unfortunately I am. For my sins, I wrote CFDP, so I'm the bad guy.
I definitely don't think you're the bad guy. I'd say you're actually the good guy here, because you've helped us a lot along the way, Di. So it's been great, really, really helpful to have you involved. Definitely not a bad guy.
Maybe. I've been ill for quite a while, so I haven't been in touch, but I'm better now, so I can get more involved. If people want to come direct to me and ask about the philosophy of the whole thing and why some things seem a bit odd, then please do.
Yeah. Yes, definitely second that. The Green Book's got some very helpful state machine diagrams and flowcharts in it, so it definitely helps with understanding. And yeah, thank you for your help there.
There is also a question in the chat pool from Nigel.
This is a question about a kind of application layer thing that is added on to the top of a lot of these protocols, called PUS, or Packet Utilization Standard, which has been is kind of put together by the European Space Agency. And Nigel's asking if we have any opinions about it. I'm aware. We're actually involved with the development of sort of PUS solution as well, not through the open source satellite. We decided to sort of move away from it for the open source satellite, mainly because it is sort of used very widely in Europe. But obviously we're trying to have a global reach with the open source satellite. So we wanted to have something which would work across, worldwide, have appeal worldwide. And the trouble with PUS is it's kind of well adopted for ESA missions, but not so well adopted across for example, with NASA and that kind of thing. So that's really the only reason we sort of didn't adopt that. Does that help, Nigel?
Yep. No, that answers the question. If there's is it planned at some point to extend the open source satellite as a sort of add-on, or is that not in the works?
Not, yeah. I mean, we're sort of developing at the moment the kind of baseline software, but software is one of those things that never ends, isn't it? There's always a roadmap, and there's always more and more things to put on top of it. So it's certainly not against the idea of adding on a sort of PUS layer, but it's not currently in the roadmap, no.
Yeah, ESA have been pushing for years to get it PUS adopted as an international standard, and it's only really supported by the EU institutions, DLR, CNES, and ESA. The commercial networks very rarely implement it. So in terms of an open, it'll be very limited as an open source asset, I have thought.
Okay, thank you.
Anyone else got any other questions? I think we're there maybe with the questions. Just wanted to say a very, very big thank you to Paul, Jamie, Brian and Andy for a highly informative talk. If anyone does have any questions, then please do not hesitate to get in touch with us. If you think of any other questions, then you can get in touch with us. And yeah, thank you very much for joining us. If you are interested in the open source satellite program, there are a number of ways you can contact us and follow along. You could simply sign up for email updates to keep up to date with what we're doing and join our monthly meetups. You can follow our social media pages, which we regularly update, and they're linked on the screen now for you. Or even better, be a guest speaker and talk about an area of interest. We would love to host more guest speakers. And next month, Vicky Anderson will be talking about architecting the open source satellite. So please join us for our next meetup on Thursday, the 14th of December at 4:30 p.m. And thank you again, and we hope to see you all next time.